Hello, everybody. Welcome to Automotive Education with Emmanuel. Today, we'll be talking about performance curves of internal combustion engines. On a base representing the engine speed in revolution per minute, are shown plotted curves of brake power, brake mean effective pressure, fuel consumption per kilowatt in brake bases, as shown in this figure. It will be observed that a minimum brake specific fuel consumption occurs at a speed of about 2600 rpm. This condition, however, corresponds to the maximum thermal efficiency over here and is most economical speed for the engine when running under conditions used in the test. As the speed increases, the brake specific fuel consumption increases and the thermal efficiency of the engine is consequently reduced. The brake power curve shows that the brake power increases with speed until the peak brake power is observed at about 4000 rpm. The maximum power output does not occur at the condition for maximum thermal efficiency. The brake mean effective pressure curve falls off steeply after the peak brake mean effective pressure has been recorded. The next on the performance curves that we'll be looking at is the volumetric efficiency curve. Now, the volumetric efficiency, normally written as VE, of an internal combustion engine is the ratio of the actual volume of charge admitted into the cylinder at standard temperature and pressure, and the suction stroke to the volume swept through by the piston. So, is the volume admitted, volume of charge admitted into the cylinder at standard temperature and pressure to the volume swept through by the piston. Volumetric efficiency is sometimes defined as the ratio of the mass of charge actually admitted into the cylinder to the mass of charge which would completely fill the swept volume at standard temperature and pressure. In a modern naturally aspirated engine, the volumetric efficiency is less than 80%. The value of the volumetric efficiency depends on several factors, including the engine speed, the compression ratio, inlet charge temperature, and mixture strength. This figure shows the volumetric efficiency in percentage plotted against the engine speed in revolution per minute. On examining the curve, it will be observed that at low engine speeds, the volumetric efficiency is slightly less than its maximum value. This is due chiefly to the valve timing being designed for a moderately high speed. Beyond its maximum value, it decreases more and more rapidly as the speed increases. This falling off at high speeds is due mainly to the increase in the frictional resistance in the inlet passages and to the excessive heating of the incoming charge, resulting in a reduced mass of fresh charge entering the cylinder per cycle. Air-fuel ratio. This refers to the ratio of the quantity of air consumed in unit time to the quantity of fuel consumed in unit time. Hence, it's written mathematically as mass of air consumed per unit time, usually in minutes, to the mass of fuel consumed per unit time, also in minutes. Now, for most petrols, the air-fuel ratio for the chemically correct, or what we normally refer to as the stoichiometric ratio of a mixture, is approximately 15 to 1. So lambda is approximately 15 to 1. This means that for the complete combustion of petrol, we need about 15 kilograms of air to burn 1 kilogram of fuel. If more than this quantity of air is supplied, the mixture is said to be weak. So if we have lambda to be greater than 1, then we say we have what we call weak mixture. But if lambda is less than 1, then we have what we call rich mixture. On the other hand, if less than 15 kilograms of air are supplied to 1 kilogram of petrol, the mixture is said to be rich, resulting in incomplete combustion of the fuel. Consequently, not all the carbon contained in petrol will burn to carbon dioxide, and therefore some carbon monoxide will occur in the exhaust. The effect of varying the mixture strength on the thermal efficiency and power output of an engine whilst running on test bench at a constant speed will be dealt with now. In this diagram, the specific fuel consumption on brake basis and the brake mean effective pressure are plotted on the same base, representing the air-fuel ratio. It should be noted that the specific fuel consumption curve is also a measure of the brake thermal efficiency of the engine. The specific fuel consumption curve is also the same as the brake thermal efficiency of the engine. Also, since the speed was maintained constant throughout the test, the brake mean effective pressure curve is proportional to the torque or power output of the engine. On the curves, you will observe that the chemically correct mixture is not the best to be employed for either economy, that is for low fuel consumption and therefore high thermal efficiency, or for power output, that is for obtaining high values of brake mean effective pressure and torque. The specific fuel consumption curve shows that for maximum economy and thermal efficiency conditions, a slightly weak mixture of about 17:1 is required. We should also note that with a weak mixture, the maximum combustion temperature is also lower. Consequently, less heat is lost through the cylinder walls. When a very weak mixture is employed, the rate of spread of the flame is relatively slow and may even continue throughout both the power and exhaust strokes. This may cause the fresh charge to ignite during the next induction stroke, resulting in backfiring or popping back through the carburetor. That's for old systems. From the brake mean effective pressure curve, it will observe that the maximum power output is obtained with an air-fuel ratio of about 12:1. That is when the mixture is about 20% rich. This is due to the partial oxidation of the carbon, producing some carbon monoxide in the exhaust gases. The presence of carbon monoxide in the exhaust during the power stroke tends to suppress a phenomenon known as dissociation. Thus, higher combustion temperatures and pressures are obtained during the stroke. The power output of the engine is consequently increased. Let us take a petrol engine under full throttle conditions at constant speed. But the mixture strength will be varied. the plot of the fuel consumption per kilowatt hour on brake basis against the brake mean effective pressure, which will be derived from the test, will give us what we call fuel consumption loop. The fuel consumption loop gives us a convenient method of studying the effects of F4 ratio upon both the power output and the fuel consumption from the viewpoint of the engine user. We should note that since the speed was maintained constant, the brake mean effective pressure is proportional to the power developed. From the graph, we will observe that for the conditions presented, the air petrol mixtures employed are very weak. Now, as the mixture strength is increased, that is from left to right, the brake mean effective pressure increases. Whilst the fuel consumption per kilowatt hour decreases until it reaches a minimum value at point A. Here, the engine is developing power by the most economical mixture. As the mixture strength is further decreased beyond this point, the fuel consumption and also the power output increase until the maximum output is reached at C. The maximum brake mean effective pressure corresponding to C is about 695 kilonewton per meter squared, and the corresponding fuel consumption is about 0.46 kilogram per kilowatt hour on brake basis. Further enrichment of the mixture after point C results not only in a greater fuel consumption per kilowatt hour, but also in the reduction of the brake mean effective pressure and consequently the brake power being developed. The effect of this is to cause the curve to loop backwards, as shown in the figure. Hence, it will be observed that for the conditions represented by the right of the graph, there are two values of fuel consumption for a given brake mean effective pressure. In that sense, the brake power as well. It is important to know at which part of the fuel consumption loop the brake mean effective pressure or brake power value is taken. The value given by the upper portion of the loop is due to an excess supply of fuel. This condition, however, is known as choking. We should note that the maximum brake mean effective pressure corresponding to point C on the graph is generally about 4% greater than the value of the chemically correct F4 ratio, which is represented on the graph as point B. That is all for today on performance curves of internal combustion engines. I hope you've enjoyed it. Like, leave your comments below, and subscribe. Thank you.